Before we get to volume, I want to talk a little bit about area under the curve and integrals. Recall that to find the area under a curve, we consider the area of a single small rectangle. And that small rectangle is going to have a width of dx if we're using a vertical rectangle and a height of f of x. So we're going to have length times width will give us the area of one single rectangle. And to get the area of the entire curve, we're going to do a summation of all of these rectangles. And that's what the integral symbol technically means. If you look at it, it's a hidden big S. It's a summation of all these areas. Now, I want you to notice in the integral that gives us the area under a curve, there's only two dimensions. You have the length or the height, depending how you want to look at it, and you have the width. And that's a concept we're used to. When we have an area of this square, we're going to multiply the length times the width. And as you'll see in a moment, when we consider volume, there is going to be a third dimension within this integral. Now let's move on to the concept of volume. Folks, volume is all about finding the area and moving that area through space. On the upper left here, we have a cube. As you can see, there's a third dimension added. So when we take the volume, we're going to find the area here, and we're going to take this area and move it through space this distance. That distance is the third dimension. Let's now look at this right circular cylinder. If we wanted to find the volume here, we would take the area of this circle and we would move it through this distance. That's the space through which we are moving it. Taking that area and moving it through space creates volume. Now, look over here with this washer. This washer, otherwise called a disc, has three dimensions and it also has a hole. Unlike the right circular cylinder, no hole, this has a hole. Here, when we consider taking the volume of a disc later on in the video, we're going to find this area here of this rim, if you will. This is almost like a patio around a circular swimming pool. That is the hole. But look, this has a width to it. So in the case of the washer, we're going to take this area and we're going to move it through space this distance. Let's first review the intuition of using a disc, or this small right circular cylinder, to get the volume of this region rotated around this horizontal line shown here. Now, the important thing to recognize is we're going to look at this small area rotated around this line. Now notice, this small area is a rectangle that comes down from the function, okay, this is f of x, to the axis of rotation. We'll call that the AOR. Notice, folks, this rectangle goes all the way to the line of rotation. And as we'll see in a minute, when we have a washer, it's going to be different. This rectangle is not going to make it all the way to the axis. But if this rectangle goes from the function all the way to the axis, there is no hole when you do your rotation, and you get this phenomenon right here. Now, to find the volume of this single disc, we're going to take the area and we're going to move it through space. The space we're going to move it through is that dx. Here, look at this right circular cylinder. We're going to get the area of this top and move it through space. That is the concept. So let's take a look at that in terms of integration. We're going to take the area of this one little right circular cylinder, this one little disc with no hole, and here it is. The volume is going to be this area times that width. That's this area taken through space, this width. Here's going to be our integral. It's going to be the summation of all of these. That's what this integral symbol means. So this is volume. Now, folks, I want you to notice we have 3 dimensions here. This area has 2 dimensions, right? We're used to that. Area having 2 dimensions. Now we're giving it a 3rd dimension because we're taking it through space. And this is the formula we're going to be using. Pi r squared, this is 2 dimensions, there's the 3rd dimension. So when we do these problems, when the rectangle comes all the way to the axis of rotation, we're only talking about 1 radius. And that's going to be the radius in our formula. So what it comes down to, folks, is finding the distance between the axis of rotation and our function. We're going to do that by using subtraction. We're going to have the top function minus the bottom function. That's going to give us this distance, which is the radius. It's just like if you want to find the difference between a child that's 15 years of age and 10 years of age. How do you do that? You take the larger age and you subtract the smaller, and you get a difference of 5. That's what we're doing here. This top function has a higher y value than this one by definition. So you do top minus bottom, gives you that distance, and that becomes the radius that is squared. Folks, let's now move on to the washer method of finding volume. Folks, if you were a contractor and you were asked to build this patio around a swimming pool, and you were charged with finding the area so that you know how much concrete to pour, how would you do it? Well, what you would do is you would pretend there's no pool there, and you would get this entire area first. And then you would figure out the area of the pool, whatever that is, and you would take the total area and subtract the pool, and that would leave you with the area of the patio. That's because there is no formula for this. So we have to take the entire area as if there was no pool, subtract the pool, that gives us the patio. So folks, to get the area of that patio, we're going to need 2 radii involved. We're going to need to get the area of the entire circle as if the pool wasn't there. That's going to be this big radius from the center of the pool out here. That's going to be big R. So that big area is going to be pi r squared. And then we're going to subtract the area of the pool, which is going to have a smaller radius. We'll call that little r. And this formula is going to give us the area of the patio around the pool. And that is going to be the concept of using the washer method to find the volume of the rotation. Now let's talk about volume with the washer method. We have 2 curves here. We have an f of x here and a g of x here. And when we go to draw our rectangle perpendicular to the axis of rotation here, we notice our rectangle does not make it all the way to the axis of rotation. Look at this, there's a space here. And when you rotate this region around the axis of rotation, that space is going to manifest in that hole. So when you see your rectangle not reaching the axis of rotation, you now know we're going to use the washer method. So here's what we're going to do. We're going to find the volume of one of these washers. How are we going to do that? We're going to find the area of that circular patio around that circular pool, and we're going to take it through a space, a distance of dx. Once we get the volume of one of these washers, we're going to do a summation and we're going to integrate from A to B. So look at this. It's the area times dx. We're going to get the area, take it through space. Here is the volume of one washer. And notice we now have 3 dimensions in this integral. 2 from the area and 1 from the width, the space that we're taking that area through. And when we do this formula to get that area, like we just spoke about a few moments ago, we're now going to consider 2 radii. Okay, so our formula now is going to be the integral of pi r squared, that's going to give us the big area, minus the pool, small area, small radius, here's big R, here's small, times dx, and we're going to sum that from A to B. So again, when you have the washer method, you're going to have 2 r's that are squared. That's because we're finding 2 areas to get the area of this patio. In our first example, we are asked to consider the region bounded by the equations y equals negative x squared plus 7, y equals 3, the y-axis, and x equals 2. Find the volume of the solid if this is rotated around the horizontal line y equals 2. So I encourage you to go ahead and try to graph this region on your own. This is going to be an upside down parabola with a width of 1, which means a perfect width, and a y-intercept of 7. This y equals 3 is going to be a horizontal line. The y-axis, of course, will be vertical. X equals 2 will be vertical, and we're going to rotate it around that horizontal line. Okay, folks, when you graph that, this is what you're going to get. Now, notice that if we go ahead and examine this region in red that's being rotated, and we draw a rectangle of rotation perpendicular to the axis of rotation, that is here. Okay, let's review this real quickly. Here's our negative or downward facing parabola. That would be a 0.7. And here's our vertical lines giving us the region that we're going to integrate. And I say that because our rectangle in this situation is vertical. How do we know that? Because you always draw your rectangle of rotation perpendicular to the line to the axis of rotation. So that rectangle is perpendicular here. That means we're going to be utilizing a width of dx. That means our integral is going to have dx in it. So if the integral has dx in it, immediately we know our starting interval and ending interval are going to be x values. So here at the y-axis, x equals 0, and we're going to be integrating to x equals 4. The other thing we know is that if we have dx, we know that this integral, the integrand, has to have x's in it. So if it has x's in it, that means every equation you use here has to be solved for y. Okay, let's now figure out how this washer fits this diagram. You could see here that this distance here, let's see if I can make this a little bigger. The distance from the axis of rotation, which is that pink dot right there. Okay, that's close enough. The distance from this axis of rotation to this white ring right there, that's the shortest distance from the axis of rotation to the region that is being rotated. Folks, this rotated region is going to create this patio around the pool. The pool is the gap. The pool is the hole. This is the region of area that we're trying to find. All right, to do that, we're going to need 2 radii. We're going to need that little small radius, which is the distance from the axis of rotation to the first part of the region, and then we're going to need the larger radius that goes from the center, from the axis of rotation to the furthest distance. Okay, so on our graph, this distance here is going to be little r, and this distance here, let's do this in pink, is going to be our big R, like so. Next, let's get expressions for big R and little r. Let's start with big R. So big R is this pink distance here. So we're trying to find the distance between that point down to the axis of rotation. Okay, this point here is illustrated by this equation, this function. So we're going to have that top function. Okay, we're going to do top minus bottom. Just like we're going to do an older girl who's 15 minus the younger girl who is 5 to get the difference in ages. Okay, so here's the older girl. The older girl is this expression. So from that, we're going to subtract the younger girl. The younger girl is here, y equals 2. When we simplify that expression, we're going to get r equals negative x squared plus 7 minus 2. R equals negative x squared plus 5. Okay, to find this little r, we're going to use the same method. We're going to take the distance between the older sister, which is y equals 3, and the younger sister, y equals 2. And when we do that, we see that the little r distance equals 1. Again, notice, all the equations we're working with are solved for solved for y. We have y equals 3, y equals 2, y equals negative x plus 7. That's because that's going to yield x's within our integrand to match the dx and to match the starting and ending point of the interval that we are going to integrate. Okay, so now that we have our small r and our big R, this one's more simplified, we are now going to build our integral. Now that we have our big R and our little r, we can proceed to build our integral. Okay, so what we're going to have is the area of the patio, the pool patio. So we're going to have pi big R squared minus pi little r squared. That's going to give us the area of the pool patio, and then we're going to multiply it by dx. Our interval is going to be 0 to 4 because we always follow what the d is. Dx means we use the x interval. Okay, so we're going to pull out a pi here, and we're going to end up with pi times the integral from 0 to 4 of negative x squared plus 5 squared, and we're going to subtract 1 squared times dx. Okay, we're going to go ahead and FOIL this. We're going to combine like terms, and then we're going to find the integral from 0 to 4. Okay, folks, so when we FOIL and combine like terms and take the antiderivative and then plug in the beginning and end, we're going to get this for our volume. 1312 pi over 15. In this example, we're given this diagram that shows the function y equals the square root of 16 minus x squared. And they've already drawn in the rectangle, and that's because they wanted us to rotate about the y-axis. And again, the rectangle is always going to be perpendicular to the axis of rotation. So the fact that this rectangle that they've drawn is horizontal, that means we're going to be dealing with a thickness of dy. If we have dy, that means we have dy in the integral. That means there has to be y's here. That means we have to solve for x. As of this moment, we are not solved for x. So let's go ahead and take the function they gave us and solve this for x. First, we're going to square both sides, and that's going to give us 16 minus x squared. I'm going to throw the minus x squared on this side and the y squared this way, and we're going to have x squared equals 16 minus y squared. Then we're going to take the square root of both sides, and when you do that, you have to add a plus and minus to the right side. So we have x equals plus or minus the square root of 16 minus y squared. Now, folks, the question is, which version of this function is it, the positive or the negative version? So my suggestion here is to look at the points that are given to us. So we have two possible scenarios. We have x equals positive square root of 16 minus y squared, or x equals negative square root of 16y squared. Let's go ahead and plug in this point, which is 4 comma 0. If we do that on the right side, we're going to have x equals 4 equals minus square root of 16, 4 equals minus 4. That's no good. Let's go ahead and just confirm that this should work out. So we have x equals 4 square root of 16 minus 0 squared, and indeed this checks out. So based on that, this is the function that we're going to be working with. So we're going to rewrite this now in terms of y, x solved in terms of y, like so, 16 minus y squared. Okay, let's get back to our integral that we're planning. The fact that we have solved for x means we're now going to look at the interval of where we're integrating from where to where. We're going to follow our dy. So we're going to integrate from y equals 0 to y equals 4. It just happens in this particular example, the x is the same, but I want you to recognize that whatever that d is, if it's dy, the interval is from the starting y to the ending y. So let's go ahead and place that in like so. Let's now go ahead and build our integral. The first thing we recognize is that this rectangle is going to be rotated around the y-axis. And when we do that, we'll see, folks, that there is no hole created. Okay? There's no hole because the rectangle goes all the way down to the axis of rotation. So all we need to do is concern ourselves with the volume of this disk, which is either a disk or a right circular cylinder, however you want to determine it. So to do that, we're going to take the area of this circular face, and we're going to take it through a thickness dy. So what is the area of that circular face? None other than pi r squared. Now, we need to find this r right here. So this r, this pink line, is the distance between this function and this function solved for x. So we're going to have the furthest right function minus the furthest left function. The horizontal rectangle has us do the top function minus the bottom, but when we're horizontal, we do the rightmost function where x is larger minus the leftmost function when x is smaller. So let's go ahead and write that down, that our r is going to equal square root of 16 minus y squared, that's this part right here, minus x equals 0. So this is our r. That is our radius. So now when we plug in, we're going to plug in this for r. So let me go ahead and erase this r squared, and now we're going to put in, we're going to take this pi and bring it out, and we're going to take this in and square it. So let me rewrite that down here in white. So we're going to have pi times the integral from 0 to 4 of the square root of 16 minus y squared times dy. Okay, simplifying the fact that we're squaring that radius means it's going to undo the radical. So we're going to end up with pi times the integral from 0 to 4 of 16 minus y squared times dy. So if we take the antiderivative of that, we're going to have pi, can't forget the pi, 16y minus y cubed over 3, evaluated from 0 to 4, and when you plug that in and do your math, the final volume is going to be 128 pi over 3 for this problem. In this next problem, we again are asked to rotate about the y-axis. We see our rectangle is drawn perpendicular to that y-axis, which means we're going to be dealing with a thickness of dy. If we have a thickness of dy, our integral is going to have dy. We need y's inside the integrand, which means we have to be solved for x. And lo and behold, they've already done that for us. So let's go ahead and rewrite the function here. Okay, folks, again, this rectangle goes all the way down to the axis of rotation. So we're just dealing with one radius. So here's our formula, pi r squared dy. In this case, our integral is going to go from the first y value to the last y value. So we're going to be integrating from 1 to 4. How do I know we're putting the y values in? Because we have dy. Next, we're going to determine the length of that radius. So the length of the radius is going to be this right function minus the left function, both of whom are solved for x. So the y-axis is going to be x equals 0. This point here is going to be our function already solved for x. So our radius is going to be this function minus 0 squared. Let's just go ahead and plug that right in because we know that the 0 is not going to play a role. So we're going to have this radius here in pink, negative y squared plus 4y squared times dy. Okay, folks, in order to do this integration, we're going to go ahead and FOIL what's in the integrand and then take the antiderivative term by term. When we do that, we have the integral of 1 to 4 of y to the 4th minus 8y cubed plus 16y squared. And when we take the antiderivative and plug in first 4 and then subtract plugging 1 in, our final answer for the volume is 153 pi over 5. The focus of this video really is setting up our integral. Taking the antiderivative and evaluating it is really not the main part of this video, but I do give you the final answer so you could check your results. Next, we are given 3 equations and asked to take the region bounded by these equations and rotate it about the line y equals 4. So I'll give you a moment to go ahead and graph that. When we do that, we get this scenario here. So 1/2 x squared is a function that looks like this. It's an odd function that's going to be symmetric in the first and the third quadrant. Here's x equals 0. That, of course, is the y-axis. Here's the cubic function I mentioned, and then here is y equals 4. So the fact that we're rotating about y equals 4 means we're going to draw a rectangle perpendicular to the axis of rotation. And we see, folks, that because the rectangle goes all the way down to the axis of rotation, there will be no hole. So we're going to use the disk method here. So our function is going to look like this, just pi r squared. Now, since it's a vertical rectangle, we're going to be using dx. So if we have dx here, we need x's in the integrand, which means we have to be solved for y, and indeed we are. Now, the next question, folks, is what are going to be the limits of integration? If we look here, that so far that is not labeled. So we want to know if we're going in the dx direction, we're going to be starting at x equals 0. But the question is, what is that ending point? So to do that, we're going to find that intersection point between y equals 4 and y equals 1/2 x to the third. So here is y equals 1/2 x to the third. Here's y equals 4. We're going to go ahead and set these equal to one another. So when we do that, we're going to multiply both sides by 2. We're going to get x cubed equals 8 and x equals 2. Therefore, we will be integrating from x equals 0 to x equals 2. Okay, next is how do we find the expression for that radius? We see we are dealing with vertical rectangles, which means we're going to have the top function minus the bottom function both solved for y. So the radius is going to be the top function minus the bottom function. And when we plug it into our integral, we're going to square it. So we're going to be left with pi times the integral of 0 to 2, 4 minus 1/2 x cubed squared times dx. Folks, we're then going to FOIL this, take the antiderivative, plug in the limits of 0 and 2, and when we do all that, our final answer is going to be 144 pi divided by 7. Next, we are given these two functions and asked to rotate the region bounded by these functions, first about the x-axis and then about the line y equals 1, and find the volume. So go ahead and graph those on your own, and when you do that, you're going to end up with something like this. So here, negative x squared plus 2x plus 4 is a downward parabola with a width that's normal. The vertex is here. It's going to have a y-intercept of 4, meaning if you let x equals 0, you're going to get y equals 4. And here's the line, y equals negative x plus 4. It's coming downhill with a slope of -1 and a y-intercept of 4. Okay, so in part A, we're going to be rotating about the x-axis. So if we're rotating about the x-axis, we're going to drop rectangles perpendicular to the axis of rotation. And you could see we're going to be working with dx, and you could clearly see, folks, that this rectangle does not make it all the way to the axis of rotation. So we know we're going to be dealing with a washer situation. Okay, let's complete the details of this graph. Specifically, the fact that we're dealing with dx means we're going to be integrating with dx, which means we want x's in the integrand. We have to be solved for y. We are already solved for y. Now, to get the limits of the integral, we're going to be going along the x direction. So the x coordinate where we start is going to be x equals 0. The question is, what's this x coordinate? We don't have that yet. So to get that, we got to figure out where these two functions intersect. To do that, we got to set them equal to one another. So let's go ahead and do that. Okay, when we move things to one side and set everything to 0, we're going to have negative x squared plus 3x equals 0. We're going to pull out a negative x, and that's going to give us x times x minus 3 equals 0. X equals 0 and x equals positive 3 are going to be our intersection points. So we now know that this is going to be x equals 3, and that is going to be limit of integration from x equals 0 to x equals 3. Now that we have our limits of integration, and we know we're going from x equals 0 to x equals 3, let's go ahead and build our integral. Folks, the fact that this rectangle does not come down all the way to the axis of rotation means this is going to be a hole. So we're going to be dealing with a washer situation. So we're going to need to find the length of 2 radii. The first radius is going to be from the center of rotation. Okay, if you look at this diagram, the center of rotation to the outer function. So that's going to be this distance, the center of rotation to the outer function. We're going to do top minus bottom. They are both solved for y. This x-axis is y equals 0. So big R in pink is going to equal this function, negative x squared plus 2x plus 4 minus 0. Okay, now little r, don't forget, is the distance from the center of the rotation, the axis of rotation, to the nearest function. So folks, that r is going to be this distance from the axis of rotation to the near function. What's the near function? It's right here. So again, we're going to get that distance, we're going to do top minus bottom, and it's going to be a small r equal to negative x plus 4. Okay, now that we know we have our 2 radii, we know that the integral for the washer method is pi times big R squared minus little r squared, and in this case it's going to be dx from x equals 0 to x equals 3. Okay, we are going to take our formulas for big R and small r and square them. So we're going to have the integral of negative x squared plus 2x plus 4 squared, that's our big R, minus small r, negative x plus 4 squared dx. Okay, folks, that is the setup. When we FOIL both of these and combine like terms, we're going to end up with this: x to the 4th minus 4x cubed minus 5x squared plus 24x. And when you go ahead and take the antiderivative and you evaluate that from x equals 0 to x equals 3, your final answer for the volume is going to be 153 pi over 5. Sorry, can't quite see that. 153 pi over 5. Okay, for part B, we're going to take the same 2 functions, the area bounded by those functions, and we're going to rotate it around the horizontal line y equals 1 like shown. Okay, we're still going to be dealing with vertical rectangles, so we're still going to be working with dx. Okay, excuse me. We're still going to be working with dx, which means we still have to have x's in the integrand and be solved for y, both of which were all set. Now, the fact that that rectangle does not make it all the way down to our axis, again, we're going to be looking at pi r squared minus small r squared times dx, otherwise known as the washer formula. Okay, so the first thing we want to do is we want to get our large radius. Okay, let me get rid of our rectangle. And we want our large radius. So large radius is going to be from the furthest function down to the axis of rotation. Okay, so this distance here is going to be the top function minus the bottom function. So we're going to have negative x squared plus 2x plus 4, that's our top function, minus the bottom function, which is 1. Y equals 1. Again, they are both solved for y. Okay, so this is going to be our big R. Okay, our small r, again, is going to be from the axis of rotation to the near function. So again, we're going to do top minus bottom. The top function is right here, this linear function. So our small r is going to be negative x plus 4. And then we're going to subtract from that the bottom function, which is y equals 1. So when we build our integral, we're going to end up with these two r's squared. So let's go ahead and do that quickly. We're going to have pi. Again, the integral is going to run from x equals 0 to x equals 3. We're going to have big R squared. That's going to be this expression right here. Negative x squared plus 2x plus 4 minus 1 squared minus little r squared, which is going to be negative x plus 4 minus 1 squared times dx. Okay, folks, we're going to simplify by adding the plus 4 and the minus 1s. We're going to FOIL. We're going to combine like terms. And when we do that, we're going to end up getting the integral from 0 to 3 times pi x to the 4th minus 4x cubed minus 3x squared plus 18x. We're going to take the antiderivative, we're going to evaluate it from 0 to 3, and our final answer on this problem is going to be 108 pi over 5.